friends, I welcome you all on India's largest live e-learning educational platform, that is Gradeup. Good evening, Ganesh, solution specialist. Namaste, how are you? Now, all of you who are joining me today, please tell me whether my audio and visual quality is okay for you so that we can proceed for the session. And till that time, let me tell you what are the topics we are going to cover today. We are going to see the voltage regulation, efficiency, auto transformer, and then we are going to take the three-phase transformer connection if the time permits. Otherwise, we are going to take it tomorrow. Good evening, Goda Kavya, how are you? All of you who are joining me, please tell me quickly whether my audio and visual quality is okay so that we can proceed for the session. Okay, Ganesh, thank you so much for reporting. Now let us proceed with the session. The first slide on your screen shows how to wash your hands so as to protect yourself and others against the infections related to the novel coronavirus. This we are communicating under the initiative started by Team Gradeup as hashtag Prep Smart Stay Safe. You should wash your hands under the direct tap water, apply soap, rub hands palm to palm, lather the backs of your hands, scrub between your fingers, rub the backs of the fingers on the opposing palms, clean thumbs, wash fingernail, fingertips, wash your hands under the direct tap water and dry it using a towel and switch off the tap by using a tissue paper or the towel, and now your hands are clean. This procedure should take approximately 20 seconds as per the government regulations. It's okay, all of you. Now focus here. Now the next slide shows the contact number for the control room which is being set up at the national level to set up to address the queries related to the novel coronavirus. You may reach this number for any guidance, support and technical queries. This also we are communicating under the initiative hashtag Prep Smart Stay Safe as started by Team Gradeup. Now before we start the session, all of you who are joining me, please tell me, I hope that you all are safe. You all are staying in your home, you all are following the government restrictions. This is very important so that we fight with this infection as a nation, united. That is important. Now the next information is about the Gradeup free of cost classes on the Gradeup classroom. In every class I used to tell this, but you are not seriously taking these things because let me tell you, I want to give you one example. I am taking this concept on fingertips classes and I think 24 lectures I have covered till now. Including the today's class, I have covered 24 lectures and I think very soon within 5 or 6 lectures, engineering ethics is going to be completed. So if you would have attended those classes, at least in this lockdown period, all the students who are preparing for engineering services, at least your engineering ethics would have completed. So don't take these classes lightly. These classes are very important. M.N. Ramesh sir, Chandan Jha sir, Rakesh Tameja sir, they are taking engineering services mains practice classes 9 a.m. in the morning. Chandan Jha sir is taking concept on fingertips classes 12 p.m. I am taking ethics classes as I already told you at 1 p.m. Monday to Friday. BYJU'S sir is taking concept on fingertips classes at 2 p.m. and M.N. Ramesh sir is taking concept on fingertips classes at 7 p.m. in the evening. Good evening, Lokesh. Venkatesh, how are you? Now there is one more important information regarding the Target Gate 2021 batch. This is an electrical engineering course and the most important feature of this course is that it is going to be a bilingual course so that Hindi or English दोनों में बातचीत होगी, so that language is no more a barrier for your learning. Rakesh sir, ME IIT Bangalore, AIR 9, 10 plus years of experience. Myself, M.Tech IIT B.H.U, 10 plus years of experience. M.N. Ramesh sir, ME Osmania University, Hyderabad, 17 plus years of experience. BYJU'S sir, 19 plus years of experience. Chandan Jha sir, M.Tech NIT Hamirpur, 9 plus years of experience. And let me tell you, more than 11,000 people have started the free trial. So if you are interested, you can also start the free trial, even if you don't go for it. Is it okay, all of you? Please tell me quickly. Are you comfortable with this information? Now let us proceed with the voltage regulation. We have discussed voltage regulation yesterday. Hello, Nabarun Das, how are you? Now just focus here. We have seen that we are going to use this approximate equivalent circuit whenever we are going to calculate the voltage regulation, and the equation that we have got for voltage regulation, you must have remembered that is Z per unit cos theta equivalent minus phi. Now this we have achieved for a lagging load condition. If it is a leading load condition, suppose you have connected a leading load and you want to find the voltage regulation, then you just replace phi with minus phi to include the leading condition. So it is going to be how much? It is going to be Z per unit cos theta equivalent plus phi. Is it clear, all of you? Please tell me quickly. Hello Malik, how are you? Now before we proceed and understand different conditions, different situations for the voltage regulation, it is very important that you understand what is this Z per unit of the transformer. Nabarun Das, definitely I will be taking HSC JE classes also, as and when it is required, when my subjects are going to be scheduled in the HSC JE channel, definitely I am going to take classes there also. Don't worry beta, don't worry. Don't lose your emotions. Definitely I will take classes in SSC JE also. When the time comes, when my schedule is there, I will take. Now focus here. The most important thing is that you understand what is this Z per unit when we are talking about the transformer. Now please try to understand this. Suppose this is your transformer. Suppose the number of turns primary to secondary is N1, N2. Suppose here the voltage is V1, here the voltage is V2, here the current is I1 and here the current is I2. I hope it is clear. Good evening Nagarjun Reddy. Now all of you listen to me. Suppose I want to use the per unit system. You must be having some idea about the per unit system, why we use per unit system, what is the significance. The most important advantage of per unit system is that whether you take the per unit impedance referred to the primary side or secondary side of a transformer, it is same. Why it is same? We want to check it. Okay. Now suppose at the primary side we are taking the voltage base as V1B and the current base as I1B. And the secondary side we are taking the voltage base as V2B and the current base as I2B. I hope it is clear. Now let me write the base impedance at the primary side. So it is going to be how much? It is going to be V1 base divided by I1 base. As simple as that. Now I am going to write the base impedance at the secondary side. So it is going to be how much? It is going to be Z2B is equal to V2B upon I2B. Yes or no? Now you just consider this. The base impedance at the secondary side. What is V2B? Can you tell me? If you have chosen the base V1B and V2B and you know this thing, that V1 upon V2 is equal to N1 upon N2. It means what? V1B upon V2B is equal to, say this is A, the transformation ratio. So this is going to be N1 upon N2 in terms of voltage base also. So this is going to be A. So you can write V2B is equal to V1B upon A. Are you getting this? Yes or no? And I am writing for current here. Suppose I1 upon I2, you are writing as N2 upon N1. You remember the MMF balance equation? So this is going to be 1 by A. So from here you can write I2 is going to be A times I1. Yes or no? Now you just put the values. So V2B is going to be how much? V2B is going to be V1B divided by A. And what is I2B? I2B is going to be, similarly you can write I2B is going to be how much? It is going to be A times I1B. So I am going to write A times I1B. It means you can write that it is going to be V1B upon I1B multiplied by, this is going to be 1 upon A square. Is it clear to all of you? Can you write this Z2B as like this? Now what is this value? This value is Z1 base. So you can write Z2 base is equal to Z1 base divided by A square. This is one relation you have achieved. Now I am going to write total impedance referred to primary side. How you are going to write it? Please tell me. Yes, Bhanu Pratap, good evening. How are you? Total impedance referred to the primary side. So this is going to be how much? This is going to be, suppose, Z1 equivalent, and this is going to be how much? This is going to be how much? Z1 plus Z2. I have told you the trick yesterday. If you are referring Z2 from secondary to primary, so from where you are referring? Z2, so keep N2 here. And where you are referring? Primary, so keep N1 here and take the square. Yes or no? So this is going to be how much? This is going to be Z1 plus A square Z2. Yes or no? Now I am going to write the total impedance referred to secondary side. So it is going to be how much? It is going to be Z2 equivalent, and this is going to be Z2 plus how much? It is going to be Z1, because now you are referring primary side for impedance to the secondary side. So this is going to be Z1. From where you are referring? Primary. So keep N1 here. And where you are referring? Secondary. So keep N2 here and do the square. So this is going to be Z2 plus, what is this? This is Z1 upon A square. Now if you take Z2 equivalent, yes or no? And you take A square as common. If you take A square as common, so this is going to be Z1, or just do it like this. You write it like this. It is going to be how much? It is going to be Z1 plus A square Z2 upon A square. So this is going to be how much? What is this? Z1 plus A square Z2. This is going to be Z1 equivalent divided by A square. Now I am going to find the per unit impedance at the primary side. Per unit impedance at the primary side. So it is going to be how much? Z1 per unit is going to be Z1 equivalent, that is the total impedance divided by base impedance. Now I am going to write the per unit impedance at the secondary side. This is going to be how much? This is going to be Z2 per unit is equal to Z2 equivalent divided by Z2B. Now you consider this Z2 per unit. Now this Z2 per unit, what is Z2 equivalent? Z2 equivalent we have found as Z1 equivalent divided by A square. So this is going to be how much? This is going to be Z1 equivalent divided by A square. What is Z2B? Z2B we have found here. Z2B is Z1B upon A square. So this is going to be Z1B divided by A square. So this is going to be Z1 equivalent upon Z1B, or you can say Z1 per unit. It means the total per unit impedance at the primary and secondary side of the transformer is going to be same. Now this we are calling as Z per unit. Is it clear to all of you? Please tell me. Are you comfortable with this? Please tell me yes or no in the comment section. Are you comfortable with this reasoning? The primary and secondary per unit impedance of a transformer is going to be same. Now this is what I mean by the per unit impedance of the transformer. And if you have any doubt, then you can ask me. Are you comfortable with this? Please tell me quickly. Okay. Now we are going to see the different conditions for voltage regulation, as you must have seen in case of a short transmission line. The first thing we are going to see the maximum voltage regulation condition. Yes or no? What is the equation for voltage regulation? It is going to be Z per unit cos of theta equivalent minus phi. Now you must be knowing this, that the maximum voltage regulation condition you will be getting for a lagging load. Lagging load condition only you will get the maximum voltage regulation, because at the lagging load you will be having the maximum dip in the voltage at the load side. So if this quantity has to be maximum, then what should be the value of this theta equivalent minus phi? This theta equivalent condition is theta equivalent minus phi, it must be equal to 0. Or you can say phi is equal to theta equivalent. Yes or no? And what is the value of this maximum voltage regulation? What is the value of this maximum voltage regulation? When this quantity is going to become 1, when theta equivalent is equal to phi, so this is going to be Z per unit. I hope it is clear to all of you. And what is the corresponding power factor? You can say at which you are getting the maximum voltage regulation condition. This is going to be cos theta equivalent. What is cos theta equivalent? This is R equivalent, this is X equivalent, this is Z equivalent, and these are the transformer resistance and leakage reactance, and Z equivalent is the transformer impedance we are saying. I hope it is clear to all of you. Yes, Gonda Kabe, you are right. And this angle we are calling as theta equivalent. Wait. So this is going to be cos phi is equal to cos theta equivalent. What is cos theta equivalent? It is going to be R equivalent upon Z equivalent. R equivalent upon Z equivalent. And this is lagging. Is it clear to all of you? Now let us see the phasor diagram for this condition. Let us see the phasor diagram for this condition, for the maximum voltage regulation condition. Suppose this is your voltage, this is your lagging current, okay, this is your lagging current I, this is your terminal voltage V, okay, and suppose this is your IR drop, okay, and this is your IX drop, and this is your IZ drop. So it is going to be, this is your IR equivalent drop, this is your IX equivalent with J drop, and this is going to be your IZ equivalent drop, and this angle theta equivalent is going to be equal to phi. That is the power factor of the load. Now you see, for this maximum voltage regulation condition, whatever voltage regulation you are getting, no approximation is required. No approximation is required. You remember that approximation or not? Please tell me yes or no. You remember that approximation? When we were trying to find the voltage regulation for any general lagging load condition, we have taken one approximation, if you remember the yesterday's class. But if you are having this condition, the maximum voltage regulation condition, theta equivalent is equal to phi, then it is not the approximation, it is the exact voltage regulation you are getting. This is very, very important point to be noted here, that the voltage regulation that you are getting is going to give you the exact value for the maximum voltage regulation condition. This is very, very important, and all of you please take note of this. This is very important because here you have not taken any you can say approximation. It is exactly coming like this. Let me correct it. Okay. So your input voltage is going to be something like this. You just assume it is to be linear. So this is going to be your Vn, which is nothing but Vn is V plus I Z equivalent. So there is no approximation. This is exact voltage regulation value you are getting. Now this may be asked in your GATE examination or the engineering services examination. So this point is very, very important. You can take note of this. I hope it is clear to all of you. Now I am going to see the second condition for voltage regulation, which I am calling as zero voltage regulation. Zero voltage regulation you will be getting in case of leading load condition. Yes or no? Leading load condition. When you are getting the leading load condition, when your phi is going to be the minus phi. What is the voltage regulation equation? Z per unit cos of theta equivalent minus phi. Now when your voltage regulation is going to be 0, when your theta equivalent minus phi is going to be 90 degree, yes or no? 90 degree, but if you are using the which equation? Lagging load condition. But you have to take the leading load, because the zero voltage regulation can only occur on the leading load. So you have to put a negative sign. So how you are going to put the negative sign? It is going to be, from here you can write this phi is equal to 90 minus, sorry, you can write it as theta equivalent minus 90 for lagging equation. But you have to take the leading case. For leading case, this is going to be phi with a minus sign. So it is going to be 90 minus theta equivalent. I hope it is clear to all of you. This is for leading case, because this equation you are using for the lagging condition. So we have converted it to the leading condition. Now let us see the power factor, corresponding power factor, and along with this you can see the important characteristics of this target GATE 2021 batch is very important. 550 plus hours of live classes, 5,000 practice questions. Can you imagine? Study notes covering each chapter and subject in detail. This is very, very important. Nobody gives this. And full length mock test, daily test and subject wise test for this. So this is something very important. Now I am going to write the corresponding power factor, and corresponding power factor cos phi is going to be cos of 90 minus theta equivalent for a leading case, and this is going to be beta sin theta equivalent. So this is going to be how much? This is going to be x equivalent upon z equivalent and leading case. This is the power factor in case of zero voltage regulation condition. Now these are the important dates. You can note down these important dates. The most important dates is 11th May, because 11th May your GEST scholarship test is going to be conducted. Is it clear to all of you? Please tell me. Now let us see for the zero voltage regulation condition, and please remember this. This zero voltage regulation we are getting from the approximate equation. This we are getting from the approximate equation. Now let us see what is the power factor. I am just doing it here. I am just doing it here so that you remember. I am just doing it here. The phasor diagram I am doing here. Phasor diagram for the zero voltage regulation condition, but by using the approximate equation. Let us see how it is going to be. So it is going to be something like this. This is your terminal voltage. This is your IR equivalent for a leading current, and suppose this you are getting as so this is going to be your V for a leading, because it is a leading current, so IR equivalent drop is also going to be leading, and this is 90 degree to this IX equivalent. And where is your IZ drop? IZ drop is going to be like this. This is your IZ drop, IZ equivalent. And where is your V in? V in is going to be better like this. I hope it is clear. Now this is something very important that you have to understand, that this is very important, that the projection of this V in is going to be equal to this V. So what you are getting as zero voltage regulation is not the exact value. You are getting it with the approximate equation. That is very, very important that you understand this. I hope it is clear to all of you. Please tell me yes or no in the comment section whether you understand this phasor diagram or not. Are you getting this? Now let us see the minimum voltage regulation condition. Let us see the minimum voltage regulation condition. Now I am going to draw the phasor diagram for the minimum voltage regulation condition. If you want to see the minimum voltage regulation condition, beta, then from this is also we are using the approximate equation. And what is the condition? The condition is that your phi is going to be minus 90, because it is going to be minimum voltage regulation you will be getting at leading case. So leading case it is minus and it is 90 degree. We'll see how. So if you put it, so what is the value of minimum voltage regulation you are getting? The value of minimum voltage regulation you are getting is Z per unit cos of, this is going to be theta equivalent minus 90. So it is going to be how much? This is going to be Z per unit. This is going to be cos theta equivalent plus 90. So it is going to be how much? This is going to be minus z per unit cos theta equivalent. Sorry, 90 plus theta, so this is going to be minus sine theta equivalent. Now what is z sine theta equivalent? You remember this impedance triangle? This is R equivalent, this is X equivalent, and this is Z equivalent, and this is theta equivalent. Okay, so what is Z per unit sine theta equivalent? This is going to be X. So this is going to be minus X per unit. This is the minimum value of the voltage regulation. All of you, please tell me, are you comfortable with this understanding? And if you have any doubt, then you can ask me. Please tell me, are you getting this or not? For a moment, I am removing my photograph so that you can see the content on the screen. And then I am going to put it again. If you have any doubt, please tell me quickly. Is it clear to all of you? Please tell me quickly. Now we are going to see the variation of this voltage regulation. Now we are going to see the variation of this voltage regulation. Just one moment. Yes. Which equation, Sanjay, beta, you want to derive? Which equation you want to derive? We have already derived that equation. I hope it is clear to all of you. Now let me tell you one more thing about this voltage regulation. Let me tell you one more thing about this voltage regulation. Let us go further. Let me write here. Let me do it here. I am saying that if you remember that for such a, you can say RL series circuit, you can also write the voltage regulation like this. R per unit cos phi plus minus X per unit sin phi. I hope you remember this equation. And if you want, then you can use this equation also for the voltage regulation. But in general, that equation that we have used, that is more easy to use in your numerical questions. That is why we are using this. I hope it is clear to all of you. So whatever equation you are comfortable, you can use it. But this equation is going to give you numericals very directly. We will see some questions also, then you will understand this. Anik Mitra is asking, sir, in transformer, why we use down regulation means this. See, beta, this up regulation, down regulation, don't get confused in this theory of down regulation and up regulation. I am telling you one simple thing. If you remember that, you will remember it always. Now see what I am going to tell you. Whenever you are going to find the voltage regulation in terms of modern methods, the modern method or the tactic is that you always represent the voltage regulation in terms of full load voltage. Whatever machine you are using, you should represent the voltage regulation in terms of full load voltage. That is the modern convention. But if you see the previous convention or the conventional way, earlier times, then we used to represent the transformer voltage regulation in terms of this equation we used to do. I hope you are clear with this. Okay, so you have to see the values given in the problem. Nowhere in the problem he is going to give you that you have to find the up voltage regulation, down. No, he is not going to ask you like this, up or down. You forget about these theories. They are not going to work. They are not going to ask question on the basis of this. They are going to ask questions. So you have to see with respect to the values given in the problem how you have to decide. Okay, I hope it is clear. We have discussed this thing yesterday. Now let us focus on one very important thing about this. We want to see the variation of voltage regulation with respect to the load power factor. This is very, very important. Lot of numerical questions can be asked on this, and you should understand it very properly. I hope it is clear to all of you. Focus here and try to listen to me properly. Beta, why you are going to differentiate it? If you are using this equation, Sanjay beta, then directly you can say the maximum and zero case. For maximum case, this cos of this angle must be 1. So this angle must be 0. If you want to take the minimum voltage regulation, then cos of this angle must be 0. When it is going to be 0? When it is pi by 2 or 90 degree. If you want to differentiate it. But there is no requirement. And this is your load power factor. Now we have seen certain points. What are those points? Let me see. When your phi is 0, you put phi is equal to 0, then what is going to be the voltage regulation? If you put phi is equal to 0 here, so this is going to be 0, sine term, sine 0 is 0, cos 0 is 1, so voltage regulation is R per unit. If you put phi is equal to 0 in this equation, this is going to be Z per unit cos theta equivalent. Go to this impedance triangle for the transformer, that is going to be R per unit. So when phi is equal to 0, at this point you are getting the voltage regulation as R per unit. When your phi is 90 degree, and this is lagging case we are taking because phi is positive in these two quadrants. In this direction phi is positive. So this is going to be the lagging case. At phi is equal to 90 degree, if you put phi is equal to 90, cos 90 is going to be 0, sin 91, and this is going to be plus sign for the lagging condition. So you are getting the voltage regulation x per unit. And this you are going to write here, x per unit. So, and somewhere between this 0 and 90 degree, you are getting the maximum voltage regulation that we have seen. Yes or no? You remember this? So this you are getting the maximum voltage regulation, something like this. So this is going to be how much? You remember this? What is the value? This value is going to be phi is equal to theta equivalent. Now I have deliberately taken this x per unit more than R per unit. But you have to check for the transformer case, but normally it is going to be the correct one. I hope it is clear. Now, if this curve is going to intersect with this phi axis, then you are going to get the zero voltage regulation. Suppose this is the zero voltage regulation, and when you are going to get the zero voltage regulation, tell me. You are getting the zero voltage regulation for which? It was 90 minus theta equivalent. You remember that? Phi was 90 minus theta equivalent for this zero voltage regulation condition. And what was the minimum voltage regulation? You were getting the minimum voltage regulation something like this. You please remember this. This is phi here. And this minimum voltage regulation you were getting as x per unit, and for this you were getting phi as minus 90 degree. This is leading case. Are you comfortable with this, all of you? Please tell me. Are you comfortable with this, beta? Jinesh Rawal, beta, who is going to teach machines in the vision batch, you can ask this question to the concerned person in the Gradeup team and they are definitely going to answer this. I hope it is clear to all of you. Now, there is some very important point out of this voltage regulation variation with respect to this power factor, load power factor. What is that important thing? Let us try to understand. That important thing is beta, that for all the lagging loads, Anik Mitra, just wait for the while, I will answer your doubt. First, let me complete this. For the lagging loads, all the time the voltage regulation is going to be always greater than R per unit. This is very, very important conclusion. You can remember this. Lot of numerical questions can be asked in the GATE examination on the basis of this information. And if you see, for all the leading loads, if you see, the voltage regulation is always going to be less than R per unit. This is very, very important conclusion. It's okay, Jinesh. You just ask this question better to the Gradeup backend team. That is going to be the better answer. Okay. Okay. Now Anik Mitra is asking very, very small question. He is asking, sir, we want at the output terminal of the transformer more voltage. No, beta, we don't want more voltage. We want the rated voltage. If in your home, suppose the rated voltage is 230 volts, for example, for a single phase supply I am telling, suppose it is 230 volts and I give you 500 volts. Are you happy? Your equipments are going to damage. Over voltage is also a bigger problem. So we don't want over voltage and under voltage. We want rated voltage. I hope Anik Mitra it is clear. Is it clear, beta? All of you please tell me. Now let us have some more elaboration on this. Okay. Let us have some more elaboration on this, then we are going to start the efficiency. Is it clear to all of you? I have to just remove something here. I will remove something here so that I can give you some important points about this voltage regulation, then we are going to proceed. The important points you please note down for the voltage regulation, all of you, that voltage regulation is an important figure of merit for distribution transformer. Why we are saying so? That voltage regulation is going to be a very important factor for the distribution transformer, because for the distribution transformer the load may vary from no load to full load. Yes or no? Now if you see, the voltage regulation is not that important merit for power transformer. What is the reason? Because your power transformer either operates at full load or not at all. I hope you are getting this. Jinesh, beta Jinesh, please control your emotions. It is better if you ask these questions to the graded team, beta. Now just focus on the class. Okay. I am going to give important things here. Now, I have said that voltage regulation is going to be an important factor when it comes to distribution transformer. It is not that important for the power transformer because power transformer is generally going to be operating in case of full load condition, not at all. Now suppose you want to improve the voltage regulation. Suppose you want to improve the voltage regulation. Yes or no? What you can do if you want to improve the voltage regulation? Please tell me. If you want to improve the voltage regulation, what you have to do? You have to reduce Z per unit, yes or no? If you reduce the Z per unit, then you can easily reduce the voltage regulation, minimize the voltage regulation, and this Z per unit is having two components, R per unit and X per unit. Now X per unit you have already minimum value you are having, because in case of transformer, this R per unit is already very small, because your transformer two windings, primary and secondary windings, they are inductive windings. The resistance part is very zero. So what about this X per unit, beta? This X per unit represents the leakage flux. Are you getting this idea? In order to improve the voltage regulation, we try to reduce this X per unit. What is X per unit? X per unit represents the leakage flux. So you have to reduce the leakage flux. So how you are going to reduce the leakage flux? There are number of ways. If you want to write, you can write it. You are going to use the sandwich windings for shell type transformer, and you are going to have height to width ratio of core type transformer is to be increased. If you increase the height to width ratio for the core type transformer, then the leakage flux is going to be less, because if you are having this kind of construction, this is the height and this is the width of the core type transformer window. So there is going to be more leakage flux. And if you are having this type of construction, suppose you are having this type of construction, if you increase the height and you reduce the width, so this is going to have less leakage flux. I hope you are getting this. So there are different ways how to reduce the leakage flux, and so that you get the lesser value of the voltage regulation. This is how we are going to conclude this. Is it clear to all of you? Now let us proceed for the efficiency. Now we have seen that efficiency of the transformer, whenever you are going to calculate, in general, if nothing is mentioned, then you are going to use this approximate circuit or approximate equivalent circuit to find the efficiency of the transformer. Why we are using this? Because this is going to represent the core losses and this is going to represent the copper losses. So in one way or the other, by using this equivalent circuit, you are actually separating the core losses and copper losses. So it is going to be easy calculation for you. So for efficiency, we are using this. I hope it is clear to all of you. Now before we understand this efficiency of transformer, let us first understand what are the losses in the transformer. I am just removing my photograph so that you can see the content on the screen. Ranjit Mel is asking sandwich type. With a sandwich type, you will discuss it later. For the time being, you can understand that sandwich, if you see the shell type transformer, so it is something like this. Okay. So this is suppose LV winding, this is HV winding, then again LV winding, then again HV winding, like this. Okay. So it is also called pancake winding. It is also called pancake winding. The basic idea to improve the voltage regulation and to reduce the leakage flux beta is, what is the idea? That anyhow the transformer windings must be as close as possible. This is the basic idea. The two winding of the transformer, whether it is primary or secondary, they must be as close as possible. I hope it is clear to all of you. Now before we start the efficiency, let us understand the losses in the transformer. The losses in the transformer you can divide under two heads. Number one as core losses and copper losses. Is it clear to all of you? Now the copper losses are nothing but your I square R equivalent losses. So you can say that your copper losses are going to be directly proportional to the square of the current, because R is going to be constant. Once you design the transformer, R is going to be a constant thing. Or you can multiply it with the voltage square. So you can say this is nothing but, you can say, the rating of the transformer. So the copper losses, you can say, they are directly proportional to the square of the rating of the transformer. This is important. Just note this down. Yes, Ranjit, you are right. You are right. Like sandwich, one by one, one by one, one by one. All these things, design purpose, you can see from the book. All these details you can see. Otherwise, if time permits, then in the last class when we are going to sum up the transformer case, then all these design details, construction details I am going to take up, because we are little running from the schedule, so we are going little faster. Now let us come to the core losses. Now the core losses beta you can define under two heads. Number one is hysteresis loss, and the next one is eddy current loss. All of you must be aware with this eddy current loss and hysteresis loss, yes or no? Now let us see it further. Now I'm going to remove this so that you understand it better. If you want to note it down, you can note it down later on. In the video, you can go backward and you can see these diagrams and all these details. Let us discuss something about this hysteresis loss and eddy current loss. Okay. Now let me put my photograph also. Now you see this hysteresis loss. Hysteresis loss. What is hysteresis loss? Please try to understand. You please try to understand what is hysteresis loss. Why we are considering this. Please try to understand. When a ferromagnetic material, or you can say magnetic material in general, when a magnetic material is placed in an external field, that is magnetic field, with frequent reversal of the field, then due to frequent reversal of the domains of the magnetic material, there is some loss in the form of, heat, you can see, and that loss we are calling as hysteresis loss. Sanjay Bantu beta, what is this proper orientation of dipoles? You please try to understand with this BH curve that we have already discussed in our previous classes. Okay, this is H, this is B, and it was something like this. Okay, now you please try to understand this BH curve, that we have said that whenever you are going to use the transformer, we are always going to use the ferromagnetic material we are going to use, that we have already discussed. And what type of ferromagnetic material we are going to use, so that, because this area is going to give the area of this hysteresis loop is going to give you hysteresis loss for one cycle of field reversal from positive direction to negative direction. One cycle, this is going to give you the hysteresis loss. So whenever you are using it for the transformer, then that material is going to be the best material which can withstand the frequent reversal of the field, because at the end of the day you are going to use the transformer with the alternating supply. I hope you are getting this. So it is going to be something like this. Even smaller, this loop area must be as small as possible for the best transformer design, to have this hysteresis loss as low as possible. I hope it is clear to all of you. Now let us see what is eddy current loss. Now the magnetic flux links with the metal parts of the transformer and gives rise to induced EMF, because your flux is going to be time variant. Flux is changing with respect to time. So when the magnetic flux linked with any metal part of the transformer is going to change with respect to time, so there is going to be some induced EMF. Because of there is going to be a conducting loop so that eddy currents flow with random directions, and this is also occurring in terms of some heat loss. I hope it is clear to all of you. Ranjit Mahal is asking, sir, how we can find that area. Beta, if you take the integration, you can find that area. Okay. So this is how we are defining the hysteresis loss and eddy currents loss. Just let us see the equation for that. Let us see the equation for that. For hysteresis loss, we are representing as PH, and this we are writing as KH Bm raised to the power n multiplied by F. This K is a constant, Bm is the maximum magnetic field density, and F is the frequency, and this n it is ranging from 1.5 to 2.5, and if nothing is given, you can take 1.6 as the standard value, and this is called Steinmetz constant. Okay, beta. So this is your equation to find the hysteresis loss, and for the eddy current loss, it is going to be Ke, another constant, and this is going to be F square, Bm square, and T square. This T is the thickness of the insulation. This can be asked in your examination. Is it clear to all of you? In general, we ignore this thickness and we simply say that the eddy current losses, we include this thickness with this constant, we assume it to be some constant value. So this is going to, because you are not going to change the thickness after once it is designed, transformer is designed. So this is going to be the equation. Now you must be knowing that if you want to represent your losses, eddy current losses and hysteresis losses in terms of voltage and frequency, the voltage, you can say it is going to be directly proportional to what? What is the equation for the voltage? Do you remember? You can say your voltage primary side, if you say, then it is going to be how much? Root 2 pi f phi into n. What is this phi? This phi is going to be Bm multiplied by the area. It means you can write your voltage is going to be directly proportional to F into Bm. So you can say this V by F ratio is going to be directly proportional to Bm. So if you put it here, so you can say that your eddy current losses are going to be directly proportional to the square of the voltage. Now in most of the transformer case, in general we keep the V by F ratio as constant. But as per the data given in the problem, you have to choose which equation you want to choose. Ranjit Mahal, what is your doubt, beta? What is exactly your doubt? Copper losses are a square of rating of transformer at full load that we have just discussed. What is your exact doubt, you tell me? What is exactly your doubt? Yes, obviously it is going to be full load condition, beta. But if you are talking about the rating of the machine. Now just focus here. What is the equation for efficiency you are going to have? The equation for efficiency you are going to have like this: output upon output plus losses. What are those losses? PC plus PCU. What is PC? PC we are saying as core losses, and this PC is going to have the hysteresis losses plus eddy current losses. And what is this PCU? It is copper losses. Okay, I hope it is clear to all of you. Now, suppose we are talking the efficiency at full load condition. So for the full load condition, if you want to find the efficiency, so this is going to be how much? This is going to be Vi cos phi, this is the output, upon Vi cos phi plus Pc plus I square R equivalent, you can say. Now there are two cases if you want to see the maximum efficiency case. In general, this is the equation for efficiency, you can say. Now if you want to see the maximum efficiency condition, I am going to remove this so that we can discuss about this maximum efficiency condition. Now better listen to me. If you want to see the maximum efficiency condition, there are two cases. Number one, case one we are taking. If load current is constant, then you are going to get the maximum efficiency in case of unity power factor load condition. So in case 1, you are assuming the load current to be constant, magnitude of the load current to be constant, and you are varying the power factor. If you see the efficiency curves, these are called efficiency curves. This is the per unit load condition, this is the efficiency value, and these are the curves you are getting. This curve number 1 you are getting for power factor 0.6, this you are getting power factor 0.8, and this you are getting at power factor 1. In terms of magnitude I am saying. So you can see, if you see for this point, the load current is constant. So for the constant load current beta, you are getting the maximum efficiency for unity power factor condition. So you have to check it whenever a question comes in the examination, especially in your engineering services or GATE examination, that if it is saying for a constant load current, then always you will get the maximum efficiency condition for the unity power factor. But suppose you are taking the second case. What is the second case? Second case is power factor is constant and you are varying the load current. So what it is going to be? Just see here. You can write beta the efficiency as V cos phi. I am keeping that I current in the denominator, so it is going to be V cos phi plus, this is going to be P C upon I plus I R equivalent. Numerator and denominator I have divided by the load current, so I am getting this equation. Now V is constant, cos phi power factor is constant. So if you want to know the maximum value of this efficiency, then what you do, you simply consider this denominator and you find the minimum value of this. Then the efficiency is going to be maximum. How you are going to find the, just I am removing this so that you can see the content on the screen. Okay. Now you see, so we are going to differentiate the denominator part. What is the denominator part with respect to I? So this is nothing but V cos phi plus, it is Pc upon I plus IR equivalent, and put it to 0. So that this denominator is minimum, so you get the maximum efficiency. Now if you differentiate, this is going to be 0, this is going to be minus Pc upon I square, this is going to be R equivalent 0. So you are getting Pc is equal to I square R equivalent. What is that? Can you tell me? This is core losses. What is this value? This is copper losses, full load. If it is a full load current, okay. If it is any other load, then also you are going to get this. Just remove this, otherwise you are going to confuse. This is just the copper losses. This we are calling as copper losses, or you can say variable losses, and this is going to be the core losses, or we call them as constant losses. Now see, in the actual reality, the core losses are not going to be constant, they are going to vary. But for the calculation convenience, we say that they are going to be constant. I hope it is clear to all of you. Now I am going to write what is the condition of load current at maximum efficiency condition. So the load current for the maximum efficiency condition I can write as I eta max is equal to under root PC upon R equivalent. Yes or no? If you multiply both sides by voltage, then it is going to be V eta max is equal to V, and this is going to be PC upon R equivalent, and here I am going to multiply I square in the denominator and I here, because it is under root, so I am multiplying with I square. Now what is I? This I is going to be the, or better write it Ix so that you understand it better. Instead of I you write it Ix so that you remember it easily. What is Ix? It is the load current at X times full load. Yes, Ranjit, you are right. I hope Ranjit among us, he can teach us machines also. So whenever I am not present, I am on leave, Ranjit is going to take classes for you. Isn't it, Ranjit? I hope you can be a good teacher, because the way you are thinking, it is very good. Now just focus here. So beta, this Vix is what? This we are calling as rating for the maximum efficiency condition, and this we are writing as the rating for the X times load, and this is going to be PC upon P copper loss at any load X times the full load condition. This equation is very important. Lot of numerical questions you can solve directly by using this equation. So if you have any doubt, then you can ask me about this equation. Just note this equation. This is very important. I hope it is clear to all of you. Now if you want to write the equation for the maximum efficiency condition, let me just write it down, then we'll go for the separation of hysteresis and eddy current loss. So the value of this maximum efficiency beta you can write as S eta max cos phi upon S eta max cos phi plus 2 PC, because core losses and copper losses are same. So this equation you are going to use whenever you are going to find the maximum efficiency condition. Is it clear to all of you? So friends, now I am going to conclude the class, because it is already 15 minutes more, and tomorrow what we are going to do, we are going to start with this separation of hysteresis and eddy current losses. From here we are going to start. So tomorrow we'll see some efficiency part, remaining part of the efficiency, then we will see auto transformer and three-phase transformer connection, that is remaining, and then we will go to the tomorrow's topic. And I think by tomorrow or day after tomorrow we will be able to cope up with the schedule. So don't worry, because we are doing it little in detail, so we are getting this. Okay, so I think by tomorrow or day after tomorrow we'll be able to match up with the schedule. So don't worry, because we are taking a lot of things in details. Otherwise we could have skipped it. But it is more important that we complete it rather than just rushing to match the schedule. So better tomorrow we are going to take up, apart from those topics, we are going to take the parallel operation of the transformer if the time permits. So don't forget to join me tomorrow, because tomorrow we are going to do a lot of things. We are going to see the remaining part of the efficiency, and then we are going to see the auto transformer. That is very, very important. We are going to see the auto transformer case, and then we are going to see three-phase transformer connection. It is also very important. It will not take too much time. Very easily we can do it. And then we are going to take the parallel operation of the transformer tomorrow. I hope it is going to be helpful for you. Thank you so much. Now don't forget to better like this page and share this video with your friends and colleagues. This is very, very important. If you want more and more such classes, then you have to share it, you have to like this page, then only we can continue with these type of classes. All of you, please tell me, is it okay for you? Now I'm going to conclude the class. Please tell me yes or no in the comment section. And better, this is the 60 plus toppers in the top 100 in the GATE 2020 examination. And if you want to be in this panel, then you have to really work hard. Then you have to really work very, very hard. Is it clear to all of you? So thank you so much for being with me on this platform. Don't forget to join me tomorrow 8:30 p.m. We are going to discuss a lot of interesting concepts related to your subject electrical machines. Thank you so much for being with me. Prep smart, score better, go Gradeup. Thank you so much, friends. And if you have any doubt, if you have any suggestion so that I can improve upon my lectures, then don't forget to tell me your suggestion in the comment box, so that for the upcoming students or the upcoming lectures, it is going to be more helpful. Okay, Gonda Kavya and all the candidates, Gonda Kavya, Ranjit Mahal, Sanjay Bonthu, all of you who are with me, Kirti Bach, Kirti Jai Bhai, all of you, Anik Mitra, Jinesh, Ranjit, Ravina Reddy, all of you who were with me in this session, thank you so much for being with me. I wish you all the best. Don't forget to join me tomorrow at 8:30 p.m. We are going to discuss really, really important topics for your subject electrical machines. Thank you so much for your time.